This is a summary of the group project Design of an Underwater Mine Detection System. Currently, the United States Navy has systems in place to detect underwater mines. However, they are very slow and very expensive, especially when compared to the low cost and low amount of time necessary to lay a minefield. The purpose of this project is to examine ways to reduce the asymmetry involved between laying and clearing underwater minefields. Underwater mines can come in various different shapes and sizes. They can be sitting on the seafloor, they can be floating on the surface of the water, or moored somewhere in the water column in between. Mines can be equipped with various types of sensors made to detonate the mine, and they can also be severely damaging to surface vessels. The picture on the bottom right is the USS Tripoli, which struck a contact mine in the Gulf War in 1991. As you can see by the picture, it caused a large amount of damage to the ship. Due to the physics of the underwater environment, the best means available today to sense underwater mines are sonar. Sonar sends out sound waves and has a receiver that senses the echoes that come back. And from those sound waves returning to the sonar, it can create a picture of the ocean floor and anything sitting on it. Currently, the Navy uses these sonars by towing them through the water with a manned helicopter. The sonar equation displays how a sonar either detects or fails to detect an object underwater. The terms in green work in the sonar's favor, and the terms in red work against the sonar. All terms are measures of sound in decibels. In the end, if the sonar excess is greater than 1, then the sonar has sensed the object. If the signal excess is below 1, that means the sonar has not detected an object. According to the Navy, the time required to clear a minefield can be up to 200 times the time required to place the minefield. The cost to lay a minefield can be as low as 0.5% of the cost required to clear the minefield. Therefore, there is a need for the U.S. Navy to improve the effectiveness of its mine clearance systems. To do this, they must reduce operational cost, increase the rate of detection, and remove the safety risk of its personnel. To begin the design of a new mine detection system, we came up with 2 sonar alternatives to evaluate. These 2 alternatives vary in size, cost, and capabilities. We also decided on these 5 alternatives to be evaluated for the vehicle portion of the system. 2 air alternatives, 2 surface boat alternatives, and 1 underwater alternative. All 5 of these vehicles are unmanned. They're able to travel pre-programmed routes through the use of their GPS, and they're all able to tow heavy loads. This diagram shows the major inputs and outputs to our simulation. The inputs are sonar and vehicle alternatives, search area, and random weather inputs. The outputs are probability detection, time, and cost. This is all achieved through the use of the probability of detection model and a system dynamics model. This free body diagram shows the forces acting on the underwater alternative as it moves through the water. The main forces it must overcome to move forward are its own drag and the drag of the sonar it is towing behind it. The drag equation and all components of the equation are shown on the bottom left. When that force is determined, it could be multiplied by distance to come up with the total energy used to travel over that distance. The forces acting on the surface alternative are very similar, with the main difference being that drag can be either due to air for the portion of the boat that's above the surface, or it can be due to water for the portion of the boat that's below the surface. Forces acting on the airborne alternative are different because of the lift required to keep the helicopter in the air. The lift equation is shown on the bottom left-hand side. The energy used to keep the helicopter in the air is added to the energy used to propel the helicopter forward to come up with the total energy used. After total energy is calculated, it can be converted to cost by first converting to a volume of fuel using the energy density of the fuel it is using, and then converting volume into cost using fuel prices. Shown here are the input parameters to the probability of detection model based on our two sonar alternatives. The main difference being the source level, which is the volume of the ping put out by each sonar. Propagation loss and noise level are random variables that change depending on the sonar's operating environment. Pairing each vehicle alternative with each sonar alternative comes to a total of 10 alternatives to evaluate. The 11th alternative is the current system that the Navy uses. All 11 of these alternatives will be put through our model, traveling in a 1 square mile area in the pattern shown on the bottom right. This table shows the results of the system dynamics model, which was all 11 alternatives traveling through the 1 square mile area. The alternative with the best fuel economy is highlighted in yellow, the small sonar paired with the underwater vehicle. The bottom row is the current system the Navy uses, which had by far the worst fuel economy. The diagram on the top shows the results of the probability of detection model. The large sonar, shown in green, had an average process signal-to-noise ratio of 30 decibels, while the small sonar, shown in yellow, had an average of 13 decibels. These average process signal-to-noise ratios were used along with the receiver operating characteristic curves at the bottom to derive the probability of detection of 0.998 for the large sonar and 0.82 for the small sonar. This value hierarchy shows the importance of different attributes of a mine detection system. These weights were derived through discussions with industry experts and then using the swing weights method. Life cycle cost for each alternative was calculated by adding up acquisition costs, operational costs, and staffing costs. Because the Navy does not publish how often they perform different operations, an assumption had to be made. Also shown are staffing requirements for operation of different alternatives. Plotting the total utility versus cost for all alternatives revealed two clear preferred alternatives circled in green, the top being the large sonar paired with the small boat, and the bottom left the small sonar with the small boat. Looking at these two alternatives together, we noticed a high difference in cost and a small difference in utility, which led us to the question, can we take the small sonar with the small boat and, because of its low cost, use multiple units at once to try to raise the total utility? This thought process led to the addition of 3 new alternatives to evaluate, all using the small sonar, small boat combination. Starting from the left, the first unit travels its pattern with the second unit directly behind it, increasing the probability of detection. The second new alternative is both units covering the 1 square mile area simultaneously, each cutting the area in half for the other. And the last new alternative on the right combines both options together, increasing probability of detection and reducing time while using 4 units simultaneously. Plotting the 3 new alternatives with the 2 previous preferred alternatives and the current baseline system reveals 2 new preferred alternatives, those being the 4 units of the small boat, small sonar combination, and the 2 units of the small sonar, small boat combination traveling in the time emphasis pattern. Our final recommendation brings 2 choices to the decision maker, either the 2-unit small sonar, small boat combination, which brings the lower cost, or the 4-unit small sonar, small boat combination, which brings a higher utility. And that concludes our presentation. Thank you for watching.